Howdy. As promised, this episode's on the physics of putters. It's considerably more interesting than I thought when I started trying to work this out. I thought it would be much simpler than it is. But let's get into it. So I'm going to take a somewhat chronological look at things, and this is my oldest putter. As you can see, it hangs completely straight downwards, and that's because the centre of mass of the putt head is not on the line with the shaft, but it's in the same, it dangles because they form a plane. And what that means in terms of physics, well, not the physics necessarily, but in the biomechanics, it means as you waggle this around, you can tell in what direction it's pointed because of that centre of mass being out there. So it feels different in your hand if it's rotated that way or that way or that way or that way. All putters were like this, so for the longest time this was just what a putter was, and nowadays these are called toe hang putters. This would be a absolute toe hang putter, this being the toe, and because it hangs down when you balance it. That's what just where the name comes from. Now, although it's the oldest design, putters of this style are still made because there are people for whom that ability to know where the club is pointing in their hand by feeling it in their hands is more important than any other technological gain they could get by switching to a different style of putter. But these aren't the most technologically sophisticated. As you can see, it's a single material head, in this case brass. That means it's got fairly uniform density throughout the material. And in fact, this one tapers down towards the toe and towards the heel, so it's actually heaviest in the middle. Now, what that means in the physics terminology is that if you took this putt head in isolation and worked out what its moment of inertia is, it's going to be relatively lower than if this middle part were somehow thinned out or, hollow, and these outer parts were bulked up. And the reason moment of inertia is interesting in putters is because there's some reason to think that when you hit the ball and you don't hit the exact centre of the club face, having a higher moment of inertia makes the putter more likely to stay straight on the line that it was originally on, which means that you lose less directional accuracy if you slightly hit when you hit the ball wrong. And the assumption is that everyone will hit the ball inaccurately in that way from time to time and to a greater or lesser extent. And we call that property of trying to make that directional miss not matter forgiveness in the parlance of golf, or that's part of forgiveness. Now, the other thing that happens when you hit the ball other than with the centre of the club is so I've said it causes the club to rotate because it applies a off-centre force which is going to cause a rotation. So that rotation changes the orientation of the club face, causing you to miss directionally. But because the some of the energy which would have gone into the ball has gone into rotating the club face, instead of pushing the ball forwards, it means the ball doesn't go as far. So you miss if you hit the ball off centre with any putter, with any current putter that I'm aware of, and I'll come back to that at the end of this video or towards the end. But if you hit the ball off centre with any putter that I'm currently aware of, you will miss it either left or right, depending on whether you missed it toe side or heel side, and you will miss it short or rather it will go less far than it would have had you not mishit it off centre. Because of that level of understanding of how putting works, putter designers moved on to making a different style of putter. We still call them blade putters, but they are actually very, very different to the sort of original type of blade that I just showed you. This would still be called a toe hang putter by modern standards, but instead of pointing like that as the original putters did, it points at an angle, not quite all the way down, but also definitely not. It's definitely more down than anything else. And there's two main distinguishing features for this. So one is there was a thought that if you got the shaft sort of line ahead of the club face, more towards where people think the ball is as they're hitting it, that would be helpful. And that's not a physics thing, that's a psychological biomechanics thing. Well, yeah, psychomechanical thing, I suppose. If it help, whether or not that helps humans' proprioception to hit the ball more accurately, I don't know. It's out of scope of this video. But the other major change is that this is not anymore a simple shape that is uniform across the or relatively uniform from toe to heel. So firstly, they've scooped a lot of material out of the centre and pushed more towards the edge, as we said they should do if they wanted to increase the moment of inertia. And the second thing is it's not a single material anymore. So I think this main shell of the head here is steel, but it's got press fit into it. I think this is a brass shim, and then I think behind these black bits is probably tungsten weighting. Certainly by the overall weight of this, I think it must be tungsten in there, and that makes this have a much higher moment of inertia, certainly much higher around the centre here, and so it should be more resistant to turning as and when you hit it off centre. Now what I observe with this putter, and I think it's because of the relatively complex shaping behind here, this was done before anyone started trying to analyse what this kind of area changes in this area of the putter would actually do, and this one gets pretty wild. You get some surprisingly chaotic behaviour from it. Chaotic meaning that very small changes in the initial conditions have very large changes in the outcome. So you can hit it from the centre and hit it a little bit off centre and get a certain result, and then hit it a little bit further off centre perhaps and get a wildly different result, and then a bit further off again you're more in line with the first one. And I will I think this is a good time actually for me to introduce, probably theoretically, why that is. So in fact there's a couple of things I've said already that if you are reasonably aware of the physics of things will have caused you to go, hold on a minute, that doesn't make any sense. So the first thing I want to talk about, well, actually they're both related, but we talk a lot about what's the moment of inertia of the club head, and we completely ignore that it's attached to this pole and then a handle. So why is it okay for us to not consider that their effect on the moment of inertia when you're striking the ball? Well, when you hit the ball, that contact time with the ball lasts for a certain length of time. It will vary depending on how hard you hit it, and also vary depending on what material the putter's made of. But as a kind of upper bound, it appears to be less than 500 microseconds. So that is half of a thousandth of a second is the longest time that the ball's in contact with the club face. And the reason you want to know that time value is because nothing in the putter can react to how you've hit the ball or where on the face you've hit the ball until at the very earliest the start of when the ball is struck. And nothing can influence what the ball, no change in the orientation of the club face or anything else that the club face does can possibly affect the ball if it occurs after the ball has left the club face. So there's that narrow window of 500 microseconds, or realistically much less time than that, during which something that happens here can possibly affect the outcome of the putt. And when you look into it, you'll find you can know what in the club can possibly affect the ball, because it depends on the speed of sound in the materials that the impact information is passing through. So the speed of sound in the metals that are commonly used for putters is up to about 3 kilometers a second, which is a lot of distance, obviously, but it's 3 meters therefore per millisecond, which means it's 1.5 meters per 500 microseconds, which is the upper bound of how long we think the ball might be in contact with the putter. And there's some good intuitive reasons for thinking that the actual length of time that matters is going to be much less than that. So firstly, in the instant when you first get contact, there's almost no force being applied either way. So it doesn't, that start of that wave isn't going to go very far just because it's so weak. So you probably only, and then the same logic applies towards the end of the putt as the ball is leaving and is barely, reducing its contact with the putter from instant to instant. Those last instants, tiny changes in what the putter face is doing are going to have next to no effect on the ball, because it's the least amount of force again, a really low amount of force being applied to the ball by the putter. So we've got this half wave shape of, there's no force initially, then you get start of force transfer, it goes up to a peak, drops back down again to zero, and then the ball is off on its way, and whatever happens with the putter after that doesn't matter. The second thing is, it would be 1.5 meters, so it's 1.5 meters from the absolute leading edge of that wave is how far that information can travel. But also, we don't care about the one-way transfer of information. We care about whether that part of the club or system, as it were, can possibly influence the outcome of the putt. So we have to we can basically half the distance that we possibly care about to 3/4 of a meter at the most, because because we know that if it the influence could only be if it takes 250 milliseconds to get somewhere, it will take 250 to get for the response to get back. And so anything beyond to 50 milliseconds distance of speed of sound from the initial contact can't possibly do anything at all during the contact time. So that cuts us from, naive interpretation of that says like everything from the center of the club face up to about here on the shaft might matter. But the other thing that is interesting with modeling it as a sound wave, any material or any object has a characteristic impedance for sound waves, and when you go through particularly an abrupt change in either what the material is or an abrupt change in the shape contours of the material, there's a tendency for that characteristic impedance to change in a stepwise form. And when you get to one of those steps in impedance, some fraction, often quite a large fraction of the energy that was was in the initial wave gets reflected back into the object that it's already in, and the rest of that energy is what gets transmitted. So what that means in the case of this putter, for example, the energy starts here and probably can flow fairly evenly throughout most of this club head. When it gets to one of these material changes, so it's going to change from steel to brass, and then it's going to change from brass to tungsten, that's going to reduce the influence those things have. So although this putter has a high moment of inertia, because so much of that comes from things that are acoustically decoupled from the impact site of the putter, it probably doesn't make as good a difference as you would hope. And then also the other discontinuity that's obvious is between the steel and the air, and you've got also these funky shapes. And I think that's what the cause is of some of the erratic putt behavior I see from this particular design. But that's also why we're allowing the second reason why we're allowing ourselves to completely ignore the shaft of the putter, because that acoustic impulse has to go from the main putt head into this narrow stem here, round this tight corner. Then there's a boundary between steel and epoxy glue, possibly with glass in it, and then there's another boundary between that epoxy glue and the chrome coating on this shaft here. Then there's another boundary between that chrome coating and probably a layer of copper, which is there as an interlayer. Then there's another boundary between that layer of copper and the underlying steel that the shaft is made of. So by the time that impulse has navigated through all of those impedance mismatches here and then 4 or 5 in there, there's very little energy is going to get through to the shaft in terms of energy that is related to the strike of the ball. And the same applies going back, that very little of that energy is going to make it through those impedance mismatches to influence the ball. So it's not the case that these parts have no effect on the behavior of the ball, but it is vanishingly small compared to the effect of parts that are in the homogeneous or acoustically coupled part of the head of the putter. And that's why we're okay to ignore it. The next two putters I'm going to show you are, broadly speaking, contemporaneous, like to each other. So this one is, broadly speaking, a debugged version of the one I just showed you. It is, as you can see, barely toe hang. It's nearly face balanced. But in this case, it's got screw-in weights that you can move around that I believe are not trying to do anything other than change that balance point, so that different players who prefer it a different way can find the balance point that they're looking for. I don't think they're trying to influence the moment of inertia of the club with these weights. I do think it's just a fitting thing. As you can see, we still have the shaft in front of the face for the psychovisual effect that has. But now, instead of the shaping behind that we had before, we've got this much more. So this area here, which is behind the part of the putter that you'll actually ever use, is very uniform. So you don't get those strange miss it a bit, you get one behaviour, miss it a bit more, you get a wildly different behaviour, miss it a bit more than that, you're back to the original kind of thing. Because the acoustic reflection of what's going on from here is going to be very consistent, because the shaping here is very consistent. And then we have a monomaterial head, so it's all one probably kind of steel, and that means, again, and with relatively smoother transitions from one part to the other, so that it should remain, broadly speaking, acoustically coupled, and the full moment of inertia of this will be delivered in a useful way to provide forgiveness. The attachment here is uncommon, right? Having this triangular truss is not a normal thing on putters, and I think I quite like it. I kind of bought it as an engineering joke because engineers love trusses, and and it doesn't seem to negatively affect the performance of the putter in this case. But you could very easily design something that looked very similar to this, but allowed all of this and the shaft to inadvertently get acoustically coupled to the strike face, and then it would change the behaviour of the putter. Not necessarily in a way that made it worse, but you would have to think about it and make sure that it was making it better before you went any further. Anyway, I believe this is still a reasonable example of what a current blade style putter looks like. And then this is the other very common style of putter, known as a mallet, and they're meant to be face balanced, meaning that the face should point straight up. And the way that's achieved is, if we look down the line of the shaft, basically the shaft, if we project it, lines up with the very centre of the, passes through a point in front of the centre of mass of the club head. Now, that means if you're expecting a toe hang experience where you're using that the toe hang experience to understand the feedback that we talked about, of where you can waggle it and know where the face is. If you're expecting that kind of behaviour, this is going to feel very wrong because it doesn't behave like in that way. But you can get used to it very quickly. There's actually no physics or mechanical engineering reason why you can't build a face balanced blade style putter, and there's no physics or mechanical engineering reason why you can't build a toe hang mallet. I think, though, that it's the reason we think of blades as toe hang and mallets as face balanced is probably because that distinction is very important in actual use. And if you had one that looked like this and was toe hang, you would probably putt the wrong way with it, and vice versa. So yeah, and again, as you can see, we are mostly a monomaterial. I think this plastic or this other centerpiece is a different material that's probably not actually involved in the strike dynamics. It's just there to give you a line to line up with. And yes. And again, we've got transitions, high moment of inertia and transitions designed to keep the acoustic coupling where we want it. I should probably explain what the idea of the phase balance putter is, really, or as I think of it, what I think the idea of them really is. So because the centre of mass is directly behind the shaft and the shaft's lined up with the ball, what it means is as you're swinging the putter down, you're kind of just dragging this mass directly behind you, meaning it will self line up to be at the face to be at right angles to that path and that centre of mass as you hit the ball. So presuming that you pass the club through the right point, because you're dragging the centre of mass behind you and that is lining the club up for you, that is kind of the aim is done by your the stroke of your putter, not by you having to orient the face in some specific way. So you no longer need to have control authority over the face direction if you're using a mallet putter. I think that's actually the underlying idea. And one of the things you'll see with the introduction of mallet putters typically is that the grips on them get bigger and softer, and the suggested technique is that you hold them more lightly, again, so that you aren't actively trying to aim the club face, you're letting the club do the work. I can understand why some people want that, because there are some people who find that if they grip the putter grip as tightly as you need to aim a blade putter, that they can't then make a smooth stroke of the putter, which means that they lose distance control if they have to impose accuracy control by a tight grip. And if you have that particular problem, then it's definitely worth trying a face balanced mallet putter. But I said there were two flaws with it, so I should explain what I think they are. So the first one is a flaw all the time. So, but particularly manifests as a problem when you're trying to hit the ball relatively hard. So I said it's self-aiming because you're pulling the putter and you don't have to hold it tightly, and it will sort of aim itself along the line that you've stroked it, and that will help you. That is true. But for most golfers, when they're putting, they move exactly the same amount. They just move faster when they need to hit the ball harder. That's certainly how I do it, and how I believe most people are trained to do it, and how most people who aren't trained do it naturally. If you aren't doing that, then this won't apply to you. But I find as I try to move faster with the mallet, with the face balance putter, as I do my backswing, I'm now pushing against this weight on a stick that I'm not holding tightly, but I can feel, because that's a very unstable situation to be pushing against that. I can feel as I take the putter back that it's always trying to turn one way or another, and so at slower speeds I find that my body will happily correct for that imbalance during the backstroke, even though it's completely irrelevant, and my conscious brain doesn't even get told that it's happening. But at high speeds, my instinctive correction of that can't keep up, and it conveys to my conscious brain as thought of we don't have control of this, we don't know where it's aimed. Of course, now that I know that this is an inherent part of the Mallet system and that it's intentionally self-correcting, I might be able to train myself to expect that and override the sort of panic uncertainty part of thing that's going on with it. Yeah, that's fine. It will correct itself as I bring the club back down. Don't worry about the face direction on the backswing. It will be fine. I haven't tried to do that because I don't personally like mallet putters for other reasons that are purely subjective, not relevant to this discussion. But I if any of you are using mallet putter and you're finding those long putts make you uneasy and therefore cause you problems, I would be very interested to know if, now that I've told you why that is and that you should expect it and that if you just ignore it, it won't be a problem. It'd be interesting to know if that helps you be more successful or be less nervous with those putts. The second flaw with mallet putters, and this will happen to anything that has either this kind of multi-bend design or the kind of separate piece going into a straight shaft up here kind of design, but shouldn't be a problem for a putter where the shaft goes straight into the head. But the problem I'm talking about is that over time these bends, or the hosel stem or whatever you call it, will bend slightly from their original shape. So when I bought this putter, it was indeed face balanced, but if I hold it like that, don't know if you can see, but it aims now slightly to the left. And that means if I use it as the original face balanced putting stroke envisaged, holding it very lightly so I'm not aiming the face, I'm just dragging the face through the ball, I will miss every putt to the left unless I compensate for that imbalance that's turned up in my putter. And this could very easily happen to you within the round of golf, particularly if you're one of those players who will lean on their putter on the greens or it gets bashed around in your bag. It's a vulnerability that the specification of the putter and it being useful at how it was designed to do is very dependent on the stability of these inherently unstable joints. And as I said, the fix for it was to take the shaft and put it straight into the head, so that, because a straight shaft that doesn't get bends in it is relatively easy to manufacture, and a socket that doesn't allow for any flexion there is relatively easy to manufacture. So if you're wondering why those centre shafted putters with the shaft straight in, which obviously removes the ability for that shaft to be ahead of the club face, the shaft line to be ahead of the club face, can't happen anymore. But that's why they came in, because it allows you to make a face balanced mallet putter that stays face balanced for its engineered lifetime rather than degrading as you use it. Now, the final thing that's only recently started to happen in putters is what they call zero torque putter, which is where instead of being face balanced or toe hanging, the putter head has no opinion about which direction it should be facing in. It doesn't settle in any one place preferentially to another. At the moment, all of the commercially available zero torque putters that I've seen are of the kind of mallet style appearance, and all of them have the shaft go straight into the putter head somewhere. Now, it's interesting that neither of those characteristics is actually necessary from an engineering point of view. here, in fact, is my 3D printed prototype zero torque blade. So I wanted it to have two symmetrical strike faces, so I can use it left or right handed, and in the same way to the old school putters. And if we look at it from the side, in fact I'll compare the two, it's actually not radically different to the original putter, except that I've moved the join from here to here. Really, that's all that is required to make a zero torque putter, is to have the centre of the shaft axis go through the centre of mass of the putter head. If you have that, you have a zero torque putter, and you can make that any shape that you want. The zero torque putter is not have any impact time physics behavior difference, so far as I'm aware. The intent with that is that it makes it easier for you to get the club face back to how you set it up, which is, well, it is physics, but it's not physics of impact. So because the putter doesn't have a opinion about which way it's facing, all that it requires is that to get to hitting the ball straight means if you set up straight and then take the club away, it doesn't really matter what you do with the club face on the way away. It completely removes any kind of opinion about what motions you should be doing, as long as what you do is bring it reverse that to hit the ball. You will hit it straight because you set up straight, you've done some arbitrary transformation on the putting face, and then you've reversed it back to where you were. In my personal testing, I found I preferred the zero torque approach because I don't have to worry about face, with a toe hang. I have to take the face open, turn the face to the right, and then bring it back facing to the left as I am hitting the ball, and I have to time that correctly. I don't have to do that. And unlike with a mallet putter, I don't have a weird feeling of inbuilt imbalance and instability on the backstroke, and I don't have to hold it loosely and trust its self-orientation on the main stroke. There will still be people who will find that they putt better with a toe hang putter. There will still be people who find they putt better with a traditional, now traditional face balance mallet, but I suspect the majority of people will find that they putt better with a zero torque putter, and so I actually expect those to become the majority over the next decade or so. That's a brief tour of the physics. As I say, when I started doing this, I thought it would be I didn't think it was going to involve the speed of sound or acoustic impedance or acoustic coupling to the extent that it did. It turns out that those things are almost the only thing that matters. Now's a good time to bring in the rules of golf as they apply to equipment. So there's limitations on what you're allowed to do with a golf club. It can't be more than 127 millimeters from head to toe, which is that dimension. It can't be more than 460 cubic centimeters in volume, whether it's solid or hollow, they don't care. There's a upper bound on the moment of inertia that the club head is allowed to have. Now, interestingly, that applies to the club head around its own centre of mass and only vertically. So theoretically I can make this club head have a moment of inertia through this line down the middle there and middle there, but around this axis of 5,900 grams per cubic centimetre. That's the number that's in the rules. And it would be legal, and if it was 5,901, it's an illegal club. So that is the rules limit on moment of inertia, which is the one I want to talk about. The other thing all clubs have to conform to, except for putters, is you're only allowed to have one striking face. With a putter, specifically, you're allowed to have two, provided that they're completely symmetrical, which is why I've built this club head to be completely symmetrical, and so that I was allowed to have two striking faces. There's a number of other rules that are important. You aren't allowed to have any concavities on the club face. It has to be convex or flat. So moment of inertia, I said I could make this have a moment of inertia of 5,900 grams per cubic centimetre. Is actual moment of inertia in the designed putter anyway is 5,750 or so. So close to, but not near enough to be dangerous to the rules limit, and close enough that it's relatively hard to make a putter of this external shape that has a higher meaningful moment of inertia. But the software I use to design this lets me know what the theoretical moment of inertia of the club head is for the rules purposes, but also I can say, if we measure it here, and rotating it about where I expect to hit the ball, what's the moment of inertia there? And with this blade style design, it is very slightly higher at this point, but still not meaningfully higher, because we're only a couple of millimeters away from where the actual center of mass is. What you'll see and it's, I guess, most dramatic on the Mallet style putters, although this isn't the most dramatic of the Mallet style putters to try this. The center of mass of this putter is it's somewhere behind the face. It's probably, let's say it's here. So that's about 10 millimeters away from where you hit the ball, instead of the 4 or 5 millimeters that I had on my blade. What that means is if they've got this to close to the limit at this point here, then when you measure its rotation about here, the limit, it will have a higher moment of inertia there than it does here, which is potentially allowing this shape of putter head to be more forgiving. Now, the reason I qualify that so heavily is I'm not happy with the assumption that the axis of rotation during the impact will be where the ball hits the face. So what I think will happen is that the actual axis of rotation is in motion within the club head during the period of time with contacting the ball, and it will start at the point of contact and it will move towards the center of mass of the combined club head and ball system quite rapidly, and then it will overshoot that and oscillate back towards that, possibly, and whether that oscillation completes while the contact is still maintained or it takes longer than that will depend on, among other things, the design of the club head and how fast you're trying to hit it. So I think probably what we should be doing, if we were trying to really exploit the rules to their maximum, we'd be looking for a design that gives us a club head of obviously as close to the rules limit as possible when measured about its own major axis. But where the front part, the part in a sort of circle or sphere around where we expect to hit the ball, has a ludicrously high moment of inertia, because that's the part of the club head that is most involved in the impact dynamics, because the forces at the more peripheral parts of the club head are necessarily more diluted and take a lot longer to transmit any effect back to the impact site. So as a working theory anyway, that's what I would like to try and do if I was trying to design a mallet. I would be aiming for, okay, I want to be within the rules, obviously, on the overall MOI, but the MOI I want to maximize isn't the total of about this axis, what's the MOI, it's the MOI in maybe this sort of half sphere volume. And that could be interesting to do a test of forgiveness versus a more traditionally designed mallet or a blade. I would do it if I was a club manufacturer trying to design putters for maximum forgiveness and wanted to be able to say I'd got something special. I would at least go and find out, does that model give me a advantage compared to the model everyone else is already using to design putters? And I would try and find a way, if it did work, to convey what that advantage is in marketing material and whatever. But as I say, it's an expensive experiment to find out, and personally, because I'm not a fan of mallet putters, just visually I find them harder to aim than blade putters. I'm not going to design and manufacture for myself such a thing, so I'm not going to do that piece of research. But I just thought I'd stick it out there as an idea. I want to talk about one more thing to do with the acoustic coupling and impedance matching and so forth. So we talked about how some of those waves, when there's a discontinuity between the materials or shape discontinuity, some of that energy will get reflected. And I know that golf club manufacturers understand this, because that's how they design their drivers, to give really good energy transfer, is by having that reflected wave, or partly it's by having that reflected wave come back and add its energy to the ball, so that more energy ends up in the ball and slightly less energy ends up in the club head than you would expect if that weren't a factor. So they know that that's how it works. And none of them have talked about the internals of their club faces, or at least not in the media that I've seen. But I suspect that the game has now changed to where they're using that acoustic reflection knowledge to make the centre of the club face relatively less efficient than they know how to do it. And then they'll make bands around that progressively more efficient in a very finely graduated way, so that at no point on the club face are you getting more efficient energy transfer than the rules allow, because there's a rule for that for drivers. But as you start to miss, what you see is, yes, you're losing energy due to that force getting used to rotate the club head in the follow through, where you don't particularly, where you would rather the energy had gone into the ball with a normal club. But because they've improved the efficiency of transfer in that off-centre position, the ball actually gets the same energy that it would have got had you hit it in the middle. So you can work out how to do that, I think, with acoustic reflections inside structures behind the club face. The rules of golf mean that you have to make the club face itself out of a single material. You can't mix and match, and there's limits to how rough you can make it and so on and so forth. You're not allowed to design things in, you can only leave milling marks or whatever. Those are what the rules say. But the advantage of messing with the acoustic reflections and other properties of the club face structures behind the club face is that those aren't covered by the rules. You are allowed to mix and match materials, which is what you need to do to be able to manipulate the reflection profiles. And that could be, well, as I say, I suspect that some club manufacturers are already doing that. Those that aren't probably will. In drivers, I think that is also something that they should be looking at in putters and working out how to explain that in such a way that they can sell putters with it. Because as I say, you do lose putt distance when you hit it off centre. And for me, if I miss by a foot to the left or degree to the left, but I got exactly the distance I was aiming for, I'd be much happier than I miss a foot to the left and also it's 5 feet short. Because the difference between those two putts to finish off is the difference between a tap in and a 50%, 60% chance of making it at my level. So it would improve my scores and much more improvement to my scores than a slight difference in driver forgiveness would give me. So actually I'd rather that's where they spent their money. Another couple of things I think would be useful to do in putter design that I haven't seen anyone doing yet, other than in one case myself. So because I was prototyping, I made it so I could attach the shaft to this putter with a screw in the same exact way, near enough as I attach driver heads to driver shafts. I don't think that's generally useful to normal people in the form that I've done it, but I think if you added in the kind of adjustment features that the drivers have, that would be tremendously useful. Because I've discovered that I need a much more upright lie angle on my putter than normal people have, which is something I was able to discover for myself because I've got a 3D printer and I'm happy gluing putters together. Normal people won't be able to do that and won't want to do that, and would think you're mad for suggesting it. But if a major manufacturer attached the shaft to the putt head with a screw-on thing that had an adjustment sleeve that let you change the lie angle, whether that's the same style as the driver where you rotate a couple of cogs, or even if it's you just need a different cog to go in there to change the lie angle from the standard 70 to the other lie angles in the legal range, I think that would be a feature worth having, because over the course of your life you may pick up back injury that means you need a more upright stance. You might pick up a back injury that means you need a slacker stance. You might want to sell the putter on the second-hand market, and then if it's able to fit anyone with the addition of a $10 sleeve or something, that's broadened the market of people who might be persuaded to buy that putter, from people who need that exact spec to people who like the look of that thing and are willing to spend another $10 to get the right adapter for them. I think also for retail, it would allow retailers to say to a customer, okay, you don't look comfortable with that 72 degree, do you want to try a more upright one or a less upright one, to just help customers get the best experience and get fit to the putter they need, without retailers having to stock thousands of every putter in every lie angle, which is just never going to happen. So I'd like to see that happen. The other thing I think is worth mentioning is although the acoustic decoupling because of the material changes is real, and it does mean that as I said, it means that the shaft has much less of an effect on the outcome of the putt than it would have otherwise. That's not the same as it having no effect, and I think it would be you should see a measurable improvement in putt accuracy for off-centre hits if you increase the diameter of the shaft and you replace they're generally speaking linearly oriented fibres with a few cross fibres to hold the thing together. It would be advantageous if they were a 90-degree crossing weave and helically wound up the shaft, at least for the first 25 centimetres or so from the club head upwards, just to make the shaft super torsionally stiff as well as relatively stiff in bending. That would improve the putt accuracy slightly but measurably. I think I'm happy to say those things would be worth doing. If I were producing putters commercially, I would build myself a putting robot and I would do those experiments and measure what the improvement was. And I think across the 3 or 4 things I've just mentioned, you should be able to measure or find enough improvement to make a fairly compelling case that you've got a putter worth people's money. I think it's worth also saying something about the effect of the ball and the orientation of the ball when you putt. Bryson DeChambeau is not crazy when he draws a line on his putter that allows him to hit a part of the ball that is a section of a sphere rather than a part that has the dimples cut into it. That is going to meaningfully reduce the number of chaos-inducing variables in the putt. It's not going to make more than, say, a few percent difference to the direction or pace that the ball goes off in, but it will make it that 2-3% more consistent, which is going to translate into some kind of sub 1% improvement in putt success rate, which doesn't sound like a lot, but when you're playing for millions of dollars, as he does, it's certainly worth doing. And if you put the work in to get used to putting with a line on the ball, why not do it like that? It shouldn't make it have enough. It shouldn't make anything worse, and it should slightly improve your consistency. Leaving the physics aside now, I want to talk a little bit about the engineering side of things. So when it comes to understanding how this is going to behave, as I said, I pretty much get what the centre of mass is, what the moment of inertia about that is, and what the moment of inertia about the strike point is for free from my CAD software. And then the next step for me has been to actually manufacture it on a 3D printer, which takes about 3 hours for that particular model in high precision. Then I have to epoxy the weights in, and wait 24 hours, and then I can physically test it. So actually, because the weights are in opposing ends and I need them to clamp under their own pressure, I have to do the epoxy in 2 days worth of work. So overall it takes about 2 days for me to go from an idea about a new putter actually drawing it up takes less than an hour typically. Then I can print it, clean up the print, epoxy some weights in, go to sleep, wake up, flip it, epoxy some other weights in, go to sleep, wake up, screw it onto the shaft and hit a ball. So I've got a 2-day iteration cycle there if I wanted to learn what I can learn from physical testing and design the next thing. Now the question I ask as an engineer is it worth my investment of time and other resources to try to build an evaluative model of the putter rather than using physical testing. And so the technique I could use, for example, would be finite element analysis of the putter, which would give me a way to, because of it being a chaotic system and so forth, I would have to have that simulate hitting tens of thousands of parts and look at the sort of aggregate distribution of those to understand if I'd made it more or less forgiving in that simulation environment. And the problem for me with doing that is I wouldn't have a way to correlate the information I was getting from that finite element analysis with real world, because I don't have a way to instrument the putter in the real world in the same way that the virtual putter would be instrumented in the FEA software. And the reason that's particularly important is that finite element analysis of collisions is notoriously difficult. What that means for me is it's not worth trying to do the simulation because I wouldn't know if I could trust it. If I were operating a proper putter design concern, doing it to make money, what you would do is you would design a bunch of a few different styles of putter that behave in a way that's notably different in the simulation software to each other, and then you would rent a high-speed camera, which you should always rent with the high-speed camera operator to make sure you get the shots and a load of lights, and I would have already built a putting robot to hit putts consistently before doing any of this. But you'd get high-speed camera footage of your putting robot hitting putts with the physical realizations of the designs that behave differently in your analysis software, so that you could compare what it looks like is happening in the real world with those designs and what your FEA's collision software is saying it thinks is happening with those designs. And you should you would hope that the FEA software already agrees with the observed reality, but you should expect that your FEA models are wrong, or some of the semi-arbitrary constants that are part of your simulation environment are not entirely appropriate for putting, because probably that software is designed for collisions of a different energy class than what you're dealing with. You need to understand how you tweak your simulation environment so that the results are real. You would not, though, want to just invest in high-speed cameras and putting robot and do everything with physical prototypes. because although those are, I think, essential parts of developing the product, if you're doing it for real, there's a massive advantage to having a finite element analysis collision simulation that you can trust, which is it will let you do a cross section of the putter and the ball during the collision and let you see what's getting stressed, where the force waves of energy are actually going, and so that your engineers can then tweak the structure to make it do exactly what you want in more conditions. Whereas if you can only observe the total outside reality, you aren't going to have anywhere near as much information, and it will necessarily be slower if you find you've got a weird hotspot on the face that you wish to get rid of. I hope this has been interesting, and the next episode, as promised, will be I will design a putter head live. I'll see you in the next one. Cheerio.